Welcome back to my YouTube channel, Steve Learning Note. We will continue our study, a roadmap to learn gRPC. In the previous video, we learned about Protobuf, a serialization technique used by gRPC. If you have not watched it, you can watch it at the link given in the video descriptions. This video is learning note about HTTP2, the transport protocol used by gRPC. Before learning HTTP2, I want to learn about HTTP1 a little bit. What are their weaknesses so that we have the successor of HTTP version 1 now? In this slide are the building blocks of HTTP1. So this is the Internet Protocol Suite model. HTTP itself belongs to the application layer. And then we have an optional TLS or transport layer security in the session layer. Commonly, we use TCP or transmission control protocol in the transport layer. So it does not have to be TCP. It can be another protocol like UDP, for example, right? Like in the one in HTTP3. And then we have IP or Internet Protocol in the network layer. In the application layer, we have the common component of the HTTP request, which consists of an HTTP request method, URL path, HTTP version, HTTP request headers, and the request body. This is sent to the server in text format. So please remember this model as we will revisit again later. In 1996, HTTP 1.0 is released. In this version, when a client wants to send a request to the server, it must open a new TCP connection. After the client receives the response, it will close the connections. If the client wants to make another request to the same host, it must open another new TCP connection again. And once the client receives the response, it will close the connection again. This process will continue until the client has downloaded all the resources. This type of connection is also being called as a short-lived connections. The pros of HTTP 1.0, I think, is the simplicity. Open, operate, close, and repeat it again, right? But there are three weaknesses in HTTP 1.0 design that I found in the analysis of HTTP performance problems that you can check on the link given in the slide. The cons is first is because frequent round-trip delays due to connection establishments. Because HTTP has no way to ask for multiple objects with a single request. Each fetch requires a single transaction. The current protocol would require a new connection to be set up. Perform slow start in both directions for short duration connections. TCP slow start is one of the first steps in the congestion control process. It balances the amount of data a sender can transmit with the amount of data the receiver can. This approach is ideal for regular connections. However, for short-lived connections, like the one that we use in HTTP 1.0, the impact of a slow start is devastating. Incurs heavy latency penalty. What does it mean? The cost of opening a new connection for each transaction requires doing a TCP three-way handshake which affects badly on the round-trip time. HTTP 1.1 is introduced in the following year, in 1997. It brings a couple of improvements and has become a standard until now, and making HTTP 1.0 obsolete. The improvement that I want to discuss in this slide is the keep alive. This feature makes the connection persistent. It is the idea of using a single TCP connections to send and receive multiple HTTP requests or responses, as opposed to opening a new connection for every single request or response pair. The keep alive general header allows the sender to hint about how the connection may be used, to set a timeout in seconds, and a maximum number of requests before the connection will be closed. The advantages and disadvantages of keep alive. The advantages are reduced latency in subsequent requests because no handshaking and no slow start anymore. Reduced CPU usage and round trips because of fewer new connections and TLS handshakes. Reduce network congestion because we use fewer TCP connections. Errors can be reported without the penalty of closing the TCP connections. Thus, another request can still reuse the same connections. And enables HTTP pipelining of requests and response. I will discuss about HTTP pipelining in the next slides, okay? So let's take a look at the cons. What is the cons? First, resource leak. So basically it is the, if the client does not close the connections when all of the data it needs has been received, the resources required to keep the connection open on the server will be unavailable, right, for another clients. So that will affect the entire systems. Second is rest conditions. So it may occur where client sends a request to the server, but in the same time, the server closes the TCP connections. HTTP pipelining. It is a feature of HTTP 1.1 which allows multiple HTTP requests to be sent over a single TCP connections without waiting for the corresponding responses, right? So in this example, the client makes 3 requests: index HTML, main CSS, and then main JS. The main CSS and the main JS requests can be sent without waiting for the index HTML response. However, the server must send its responses in the same order that the requests were received. So the entire connections, basically, it is a first in, first out. One of the pros of pipelining is a dramatic improvement in the loading times of HTML pages, since multiple requests can be sent in parallel. But we have the cons. The cons of the pipeline are, first, it's a head-of-line blocking. A performance limiting occurs when a line of packets is held up in the queue by a first packet. So a single slow response will block all requests behind it. So that's what head-of-line blocking means. Second, when processing in parallel, server must buffer pipeline responses which may exhaust server resources. And the last is a failed response may terminate the TCP connections, thus forcing the client to re-request all the following resources, which may cause duplicate processing. Due to complications, HTTP pipelining adoptions has remained very limited despite its many benefits. Most browsers nowadays disable these features. There are several techniques to alleviate performance issues in HTTP1. The first one is using multiple TCP connections for the same host. Since the pipelining is disabled by default, modern browsers use a parallel TCP connection as the workaround to the performance issue. However, there are several considerations and limitations for this performance tweak. The first one, there are limits to the number of concurrent TCP connections that is possible between a client and server. Each new connection requires significant resources on the client and also on the servers, and maybe in between, in the intermediaries, which means they need extra memory buffers and CPU overhead. The next one is resource inlining. Resource inlining is an optimization that helps reduce the number of outbound requests by embedding the resource within the document itself. For example, if a client needs a specific CSS file to render a page, inlining that CSS file will provide the client with the needed resource before it asks for it, reducing the total number of requests that the client must send. However, there are several considerations and limitations too. Like larger files in non-text formats can greatly increase the size of the HTML document, which can ultimately decrease the connection speed and nullify the original advantage gained from using this technique. The client cannot separate the resource and the document, right? Because those now become inlined. It means that the client cannot decline. The client cannot decline resources that it already in the case, right? The third one is concatenation and spreading. It is a technique to bundle multiple resources into a single network request, which reducing the network overhead cost. Concatenations means multiple JavaScript or CSS files are combined into a single resource. Meanwhile, splitting means multiple images are combined into a larger composite image. There are cons for these performance tweaks. The first one, introduce extra application complexity by requiring additional pre-processings and also deployment considerations and code. For example, like we have to prepare extra CSS code or markup for managing the sprites. Combined bundle may contain resources that are not required for the current page. A single update to any individual file would require invalidating and downloading the full asset bundle, resulting in the high byte overhead costs. Both JavaScript and CSS are parsed and executed only when the transfer is finished, potentially delaying the execution speed of your applications. In early 2010, Google created an experimental protocol called SPDY or SPDY, right? It pronounced SPDY. The purpose of the new protocol is to make the web page load faster. Later, in May 2015, it became a new standard and the next version of HTTP. I hope you still remember this Internet Protocol Suite model. And I want to introduce to you something difference between HTTP2 and 1 in this model. The binary framing layer is the most significant features that distinguish HTTP1 and HTTP2. Unlike HTTP1, which keeps all requests and responses in plain text format, HTTP2 uses the binary framing layer to encapsulate all messages in the binary format while maintaining HTTP semantics such as verbs, methods, and headers that we already familiar in the version 1. These new improvements, the binary framing, will allow HTTP2 to make the performance far better, which is we will look at in the following slides. What are the performance improvement gains from HTTP2? HTTP2 establishes a single connection object between the two machines. Within this connection, there are multiple streams of data. Streams are bidirectional connections, and they may carry one or more messages. Each stream consists of multiple messages in the familiar request or response format. Finally, each of these messages is split into smaller units called frames. The frames is the smallest unit of communication that carries a specific type of data, like HTTP headers, message payload, and so on. And each frame will have a tag by the stream ID. One binary frame contains a frame header and the frame payload. The payload of the frame depends on the frame type. For example, I have a frame with the types headers, which contains the HTTP header information that we are already familiar with. The frame header is a 9-byte header that contains the length of the frame type, flags, and also the stream identifier. This is the list of frame types. You can look into it more detail in the link given in the slides. For example, a frame type data used to transport HTTP message bodies, which allow payload of up to 16 megabytes per frame. Okay, let's talk about multiplexing. The binary framing will identify each frame to a particle stream. It allows the connection to interleave these frames during transfer and then reassemble them at the other end. The interleave request and response can run in parallel without blocking the messages behind them, and this process is called multiplexing. This slide shows multiple streams in flight within the same connections. The client is transmitting a data frame stream 5 to the server, while the server is transmitting an interleaved sequence of frames to the clients for stream 1 and stream 3. As a result, there are 3 parallel streams in flight. Multiplexing resolves the head-of-line blocking issues in HTTP1 by ensuring that no message has to wait for another to finish. Multiplexing can deliver lower page load times by eliminating unnecessary latency and improving utilization of available network capacity. It means we can remove unnecessary HTTP1 workarounds that I have shared with you before. Once an HTTP message can be split into many individual frames, and we allow for frames from multiple streams to be multiplexed. The order in which the frames are interleaved and delivered both by the client and server becomes a critical performance consideration. Stream prioritizing is a feature to control message resource allocations, such as CPU, memory, and other resources, and also to control the order by giving them weight and dependency. In the illustration, the channel contains 6 streams, each with a unique ID and associated with a specific weight. We can assign a weight between 1 and 256 to each stream. The higher the number indicates higher priority. Stream 1 does not have a parent ID associated with it and is by default associated with the root node. All other streams have some parent ID. The resource allocation for each stream will be based on the weight they hold and the dependency they require. Stream 5 and 6, for example, which in the figure have been assigned the same weight and the same parent streams, will have the same prioritization for resource allocations. To make it more clear, let's convert this into a tree. In this dependency tree, stream 1 depends on the root stream, and there is no other stream derived from the root. So all the available resource will allocate to stream 1 ahead of other streams. Since the tree indicates that stream 2 depends on the completion of stream 1, stream 2 will not proceed until the stream 1 task is completed. After stream 2 complete its task, stream 3 and stream 4 will get the resources. They are split in the ratio of 2 and 4, as indicated by their weights. Stream 3 will get 34% resource allocations, and stream 4 will get 67% resource allocations from the available resource. Finally, when stream 3 finishes, stream 5 and 6 will get the available resource in equal parts. They do not have to wait for stream ID 4 completions. Since HTTP2 enables multiple concurrent responses to a client initial GET request, a server can send resource along with the requested HTML page, providing the resource before the client asks for it. This process is called server push. After the server receives the index HTML request, it will notify the client that the server We'll also send script.js and style.js, style.css, by sending a push promise frame type for each resource. The client can accept it or reject it. If the client decides to reject it, maybe because it has the resource already in the cache, the client will send the RST stream type frame to the server. These features can eliminate the need of resource inlining in HTTP1. In August 2022, Google Chrome decides to disable the server push. The main reason is that it was hard to implement and the performance benefits were often difficult to realize. As a result, it was not used much, with only 1.25% of HTTP2 sites making use of these features. As an alternative for it, Google recommends 103 early hint or preloading critical resources. In HTTP1, the header component is always being sent in text format, while the data itself, the payload, is compressed by programs like Github. This causes overhead on performance, especially when we need to send HTTP cookies header, because the size will be bigger. To reduce this overhead and improve performance, HTTP2 will compress request and response header metadata using the HPEG compression format, which it will reduce their individual transfer size. Additionally, HPEG can keep track of the previously conveyed metadata fields and further compress them according to a dynamically altered index shared between the client and the server. It requires that both the client and server maintain and update an index list of previously seen header, which is then used as a reference to efficiently encode previous transmitted values. In other words, the second request will only send the payload in the header that is not in the list before. So it's more small and more efficient. Thank you for watching. I'll see you again in another learning video. Until then, stay healthy and stay learning. Bye bye.